Okay, chapter 4 from the textbook is all about a very common and actually very popular statistical procedure known as regression. Specifically, a type of regression called linear regression. There are multiple different forms of regression. We're going to deal with the really the most basic and the simplest form, and that's called linear regression. Linear means straight line, okay, or refers to a straight line in this case. All right. So in this chapter, we're going to talk about what's called the least squares regression line. We'll see that here in a moment. We're going to look at how you find that line running through a scatter plot of data points. We're going to look at a statistic that helps us to basically quantify or measure how much of the variation in a dependent variable can be explained by an independent variable that's known as r squared. We're going to look at the effect on a linear regression of outliers and influential observations. We're going to see how you can use regression to make predictions. That's actually one of the most useful aspects of regression. And then talk about some sort of pitfalls that we have to be able to, or have to hopefully avoid, having to do with causation and association and that sort of thing. Anyway, all right. So let's talk about the regression line first. So remember in chapter 3, we talked about correlation. And in correlation, we were looking at the strength of a relationship between an independent and a dependent variable, an explanatory and a response variable. And we looked at that in terms of scatter plots. And we calculated what was called R, the correlation coefficient, which was basically one number that gave us a good feel for how strong or weak the relationship was between an independent and dependent variable, and also the direction of that relationship, positive or negative, if you recall. With regression, we're going to take correlation one step further. We're going to, using a scatter plot, create what's called the least squares regression line. It's also called the line of best fit. Let me write that down here. Line of best fit, okay? And you see a line of best fit right there. So this line of best fit is the line that most accurately describes the relationship between some independent variable and some dependent variable. In this example, we have number of beers consumed versus blood alcohol content. We saw that in the last chapter on correlation. And here's the scatter plot that we have from that. But now you see we have this linear or this straight line, the line of best fit, running through that data. So that line has a particular slope, which is an important descriptor of that line. But also you see that in most cases, these data points do not fall on the line, right? There's some distance above it or some distance below it. The distance above or below, or in other words, the distance or how far a data point is from that line, is called the residual. So what you see here is the residual for this data point. Here you see the residual for this one. This residual is positive, it's above the line of best fit. This residual is negative, it's below it. So the least squares regression line is the unique line such that the sum of the vertical distances, the sum of the residuals, and the line is 0. So if you add up this positive, this negative, this negative, this positive, if you add up all these residuals, that line is positioned such that if you add up all those values, you get 0. If you square all of those residuals and add them up, that value is the lowest it can possibly be. It's easier to think of it not in terms of squared residuals, but just residuals alone. And positive and negative, you add them up, you get 0. That tells you the line is in the correct place. Okay. So, as far as some important notation here, okay. Oops, sorry, wrong. All right. So we have this statistic called y hat. Y hat is the predicted value of y, okay, on the regression line. So here you see how we denote y hat, y with a little caret symbol above it. That equals our slope plus our intercept, okay? So the intercept plus the slope, and then the slope multiplied by x, which is going to be some value of our independent variable, that's what gives us a predicted value. In statistical notation, this is the equation of the line, y equals a plus bx. You, from algebra, probably would better recognize this as y equals mx plus b. This is the notation you generally see in an algebra course or a calculus course or something like that. This notation is the same thing. It's just statistical notation. So y equals a plus bx. So x is some value of your independent variable, number of beers consumed, for example. B is the slope of that regression line. A is the y-intercept. You do the math here, and it spits out a predicted value of y, a blood alcohol content that results from those number of beers consumed. Now, this slope, B, can be either negative, slopes downward. It can be 0, meaning horizontal, or it can be positive, meaning it slopes upward. If you have a slope of 0, that means there's no relationship between your x and your y variable, because it doesn't matter what the value of the x variable is, that always gives you the same y value, same value of y. So that means there's no relationship because y doesn't change as x changes. It's only here with a negative slope and here with a positive slope that you have a relationship between your x and y variable. All right, so again, the slope of the regression line tells us how much we would expect our dependent variable to change on average, that's important, on average, for every unit change in our independent variable. So here with number of beers consumed, okay, you see as we go from few beers to more beers, the blood alcohol content goes up. We have a positive slope to our line. That slope tells us on average how much a 1 to 2 beer increase or a 2 to 3 beer increase, on average, how much of an increase that should result in terms of our blood alcohol content. The intercept, if you draw the line all the way to the y-axis, where it intercepts, the y-intercept is just a mathematical description of the regression line. It's important because it places that regression line vertically along the y-axis, but it's not describing any property of the data. Okay, the slope does that, the y-intercept does not. Okay, so how do we calculate the slope of the regression line? Well, first of all, let's just say that typically you can do this with a stats calculator, or you just let a software program like Minitab do that for you. But in a pinch, you can calculate it yourself. So the slope, and again, I have to write these things in because they don't transfer on the iPad. The slope, B, equals the correlation coefficient multiplied by the quotient of the standard deviation of our dependent variable and the standard deviation of our independent variable. So if you know what the standard deviation of your y data is, you can divide that by the standard deviation of your x data, take that quotient, multiply it by your correlation coefficient, and that gives you the slope of the line. Now, the intercept, the y-intercept, A, that equals the average of our y data, so y bar is average of our y data, minus the slope times the average of our x data. So you have two columns of data, x and y. Take the average of x, multiply that by the slope, take that product and subtract it from the average of your y data, and that gives you the y-intercept. All right. So again, you can calculate these by hand. You should be able to do that as well. Okay, so you should take practice with that to a certain extent. All right. So how do we plot this least squares regression line? Sorry about that. How do we plot this least squares regression line? Well, again, typically we'll have a software package do this, but let's say you're doing this by hand. You have a scatter plot and you want to sort of estimate where that regression line is. You could freehand it, although that's not the easiest to do in a lot of cases. What you could do is if you know what the regression equation is, and you see the regression equation right here, okay, the line of best fit equation, you can use that to find two extreme values. So let's say take 8 beers, for example. Take 8 and plug it in right there as your x value, work out the math, and you get a predicted value of y. So you plug in 8, you get 0.116 right there, 0.116 on the y-axis. You could also take and plug in a value of 1 right there. Plug it in here, work out the math, you get another value. Well, I'm sorry, here's the equation for it, 0.0152 right there. So 1 and 0.0152 is one xy pair for that data point. 8 and 0.116 is another xy pair for that data point. Simply draw a line between them. That gives you the regression line. And that regression line should run through, in the center, the average of your y data and the average of your x data. This is the center point, or the pivot point of that line. It's centered on the average of y and the average of x. Okay. Now, these 2 points we've just come up with here, they're not actual data points in our data set. We made these up to allow us to draw a line between them. That's an important point, okay? All right. Now, I mentioned before at the very beginning that there are multiple types of regression. What we're dealing with is called linear regression, okay? There's something called nonlinear, there's polynomial, various other types of regression, more complicated. We're dealing only with linear. So it's important to recognize that you can only apply linear regression to a data set where the relationship between your x and y variable is actually linear. Well, how do you know that going into it? You have to plot the raw data first, always. Always do a scatter plot and make sure that the scatter appears linear before attempting linear regression. So, what do I mean by this? Well, take a look at all these different data sets, A, B, C, and D. If you do linear regression on all of these, they all give you exactly the same equation for the line of best fit. All right, so that's one thing. But then when you actually plot them, what do you see? You see they're not all linear. Data set A is actually linear. There's no obvious curve to the spread or the pattern of that scatter plot. Data set B is clearly curved, nonlinear. Data set C has an obvious outlier here, which means that you need to look at that. Is that a recording error? Is it something you can get rid of? What is the deal there? Okay, you need to look at that. Data set D only has 2 X data points, this one and this one. This is going to require a collection of more data or a redesign of the experiment. Only data set A is appropriate for linear regression. This is why you have to plot it. Because again, each one of these data sets gives you exactly the same formula or equation. All right, let's talk about the coefficient of determination, R squared. So R squared is just the correlation coefficient squared. So in chapter 3, we went over how to calculate the correlation coefficient. For regression, you just square that number, and now you've got R squared, what we call the coefficient of determination. So what does this tell us? This is what it tells us. It tells us what proportion of the deviation of our predicted values from the average of y is explained by x. So look at this scatter plot over here. So we have our scatter plot, the blue points. We have the red line indicating the average of our y value, right? And we have the residuals here. I'm sorry, not residuals. We have the deviations from the regression line to our average of y shown in these green arrows. So here we have a hypothetical data point for our regression line. The distance from it to the average of y is what this arrow is telling us. All right. Well, by the way, that's the minus sign there. So if we look at this plot below, we can see our actual residuals, right? Sorry, these aren't residuals because that's the average over y. We can see how much each data point deviates from the average of y. So here's our y data, 0.065 maybe it looks like is the average there. And so you see this data point being 0.12 has a large deviation from that average, as does this one down here. The regression line that runs through that, all right, encompasses this much area, or this much of our deviation. This deviation that you see right here, and also right here, that is not encompassed by our regression line. So that's variation in our Y data that cannot be explained by our X data. That's variation in blood alcohol content that cannot be explained by the number of beers consumed, right? So this is variation having to do with, for example, body weight, metabolic rate, whether or not somebody ate a meal before they started drinking, that kind of thing. It's only this variation between our average of Y and our regression line that can be explained by the model. R squared is that proportion, okay? So here we have an R of 0.87, a correlation of 0.87. You square that, R squared equals 0.76. That means that this particular regression model explains 76% of variation in blood alcohol content. If you know how many beers somebody's consumed, that variable alone explains 76% of variation in blood alcohol content. That's what this means. That's what R squared tells us. Obviously, the higher that number, the better the predictive value of that model, the more information we have, the more variation in Y we can explain. Let's look at some examples. So here we have a scatter plot. Looks like it might be roughly negative, not a very good correlation at all. Correlation is minus 0.3. Square that, coefficient of determination, R squared, is 0.09 or 9%. Whatever this X variable is, it only explains 9% of the variation in the Y variable. Here, much better association, correlation of minus 0.7, R squared 0.49. So whatever X is, it explains 49% rather of variation in Y. Here, really good, very tight association between X and Y, R squared of 98%. That's good. I mean, if you're trying to predict some value of Y from some value of X, you want to have that R squared value being as high as it possibly can be. All right, what about outliers and what we call influential data points? So we saw in an earlier chapter that an outlier is simply an observation that's going to lie outside the overall pattern, right? So here, child 19, for example, using the Giselle adaptive score data set we looked at before, sits very high above the regression line. It's not within this channel or pattern of the data. Here we have child 18, which is way out here to the end. And we talked about the reason for having very little data here. So we've got these big gaps, and then this one, which seems to be sort of away from the center of mass of the data, is still within the pattern because it's close to that slope of that line, but it's just far down the line. That could be an influential data point. An influential data point is a data point or an observation that can dramatically affect the regression line, the slope of it, if it's removed. So we'll see what I mean by that in a minute. An outlier doesn't necessarily do that. It wouldn't necessarily strongly change the slope of the regression line if you remove it. An influential data point generally will. All right, residuals. We talked about residuals a little bit already. Again, the residuals are just the vertical distances of each data point from the regression line, called residuals. Remember, if we have our regression line in the correct place and with the correct slope, then the residuals should add up to 0. The positive values will cancel out the negative values and vice versa, and you'll get 0, okay? So basically, the residuals in a really good regression model where you have a high R squared are going to be very low. That means that all the data points will be very close to the line. In a situation where you have a fairly low R squared, a model that's not going to be very good for predicting some value of Y from a value of X, you'll have high residuals. They'll be widely spread above and below that line. All right, so the residual then is the distance between the observed value of Y, your actual data point, and the predicted value of Y. Predicted values are always going to be values on that regression line. So let's look at the effect then of outliers and influential data points on the slope of the regression line. So go back to that data set with the Giselle adaptive score and age at first word. So here we have 3 different scenarios. So the solid red line is our regression line with all the data considered, okay? The influential point and the outlier. You can see the slope of that line. Now, let's say we take child 19 out. So let's say we determine this is an outlier and we chuck it, we get rid of it. The black line now, the new black line, or the black line is our new regression line. And you see it reduced the slope a little bit, but not very much compared to what it was, that distance there. But put that child 19 back in, and then take the influential data point, child 18, out. Now you see what has happened to our regression line. It changed it dramatically. So that's changing the equation of the line. And if you try to predict the Giselle adaptive score here with and without child 18, you might get drastically different results because it changed the slope. That's why child 18 is considered an influential data point, because it can dramatically affect the slope of that line. We have to be careful about those and understand what it is they can do to a regression line. Now, what about making predictions? So I said earlier, this is one of the most useful aspects of linear regression, or any kind of regression. So we can use the equation of the regression line to predict a value of y for any value of x, but importantly, within the range studied. So this is called prediction within range. So if we have a number of beers here between 1 and 8, you can predict, you can use this equation, the equation of this regression line, right here, sorry, let me fill it in, to predict any value of blood alcohol content for anyone who has consumed between 1 and 8 beers. You wouldn't want to do it for 10 beers, and you wouldn't want to do it for less than 1 beer, okay? All we know is that between 1 and 8 beers, the relationship is linear. It may not be linear above that, and it may not be linear below that. We don't know, we don't have data. So we need to predict within the range of our data. Predicting outside the range is called extrapolation, and that can lead to spurious results because you don't know what's going on up here, and you don't know what's going on down there. All we know is what's going on here. All right, so let's take a look over here, for example. All right, first of all, let me fill this in. Okay, so what will we predict for someone who consumed 6.5 beers? Well, this is our regression equation. We need to plug in 6.5 right there for our value of x and work it out. And we do that, we see we get 0.0944. So what is that doing? Well, basically it's saying, well, we have 6.5 beers, draw a vertical line up until you hit the regression line. From that point, go over left to the y-axis, and wherever it intersects, that's the answer. 0.0944 is the average blood alcohol content for somebody who consumed 6.5 beers. That's one of the really useful aspects of regression, is to be able to predict in that way. But again, we always have to do it within the range of our data. All right, let's look at some other examples here. Okay, here we see number of powerboats registered times 1,000. This is in Florida, times versus number of manatee deaths. We have a linear relationship. You can tell that by the scatter of points. There's our regression line right there. This is our data set over here, okay? This is the equation of our line. See, we have an R square of 91%. That's pretty good. Generally speaking, you want to have, there's no hard and fast rules, but a good rule of thumb is 70% or better for your R squared if you're trying to predict. 70%, all right? So the equation for our line then is y predicted equals 0.1301 times x minus 43.7. So question is, if Florida were to limit the number of powerboat registrations to, say, 500,000, what could we expect for the number of manatee deaths in a year? Well, 500,000 is going to be, right there. Draw a line up, go over, should be right in there. Let me fill this in. So here we have our equation, okay? and that's going to give us 21.35. About what I said, 21.35. Roughly 21 manatee deaths. Okay, so could we use this regression line to predict the number of manatee deaths for a year with 200,000? Well, you notice that our data, all right, in terms of powerboat registrations, the smallest number we have is 447,000. So right there. So now we're predicting down here for 200 somewhere. So yeah, 200 would be about right over here, 200, 400, 600 right there. What does that line do? Well, as you're going to see in a minute, we wouldn't want to use this regression model to predict the number of manatee deaths for 200,000 powerboat registrations, because that would be prediction outside the range, extrapolation again, right? Trying to extrapolate down here. And in this case, if you did that, extrapolation gives a nonsense prediction of minus 17.7 deaths, because before that regression line hits the y-intercept, it dips below the x-axis, giving you a negative value. All right, as you see right there. So here we have 200,000 powerboat registrations. So you go over, and it's a little bit off, but it's actually minus 17. Okay, so that makes no sense. That's again the danger of extrapolation, predicting outside the range. Clearly, you can't have negative 17 deaths. That would mean that any single powerboat below 200,000, or actually below whatever this number is, probably 300,000, would actually increase manatee births. That makes no sense. All right. Let's look at another example of extrapolation here. So here we have just a random data set. Doesn't have to mean anything necessarily. If you plot that data in Minitab, you get a plot that looks like this. Now that looks pretty good. That's a fairly linear relationship. You see that the R squared is 98.1%, and you see we have our equation here of our line. Okay, now what if we wanted to know the value of y for an x value of 14? So 14 might be what? About right there, okay? You plug in 14 for your x, and you get 1064.35. Okay, that is what it is. Doesn't look crazy. Now, on the other side, what if we wanted to know the value of y for an x value of 4? Well, 4 is going to be, what, here somewhere. All right, plug it in, gives you a value of 165.98. Well, what's the problem with that? We only have this data here. If we had the rest of this data, below and above, you would see that the line actually, or the relationship is actually not linear. It's complex, it's curved. So we were predicting using this data here, which it indeed looks linear. But our value above at 14, the predicted value turns out to be there because, look, that regression line would go that way if you're just using this, right? It predicted here, when in reality the data does this. That is way overestimating whatever the value of y is. Our predicted value down here falls in the regression line, but you see that the data points are actually below that. So this is why you don't predict, you don't extrapolate, you don't predict outside the range, because you don't know what's going on outside the range of your data. All right. Last thing to talk about is the danger of not understanding that association does not always imply causation. Just because it seems like there's a relationship between our x and y variable, that doesn't mean that x is actually causing y to change in a predictable way. It could be that there's some third-party variable, some external cause that's causing this apparent relationship between x and y. This is what we call a lurking variable. It's a variable that is not among the explanatory or response variables in our data set, but may influence the relationship between these two variables, making it seem like there's a relationship between them. Whenever that happens, whenever we have an apparent relationship between an x and y variable that is being affected by a third-party variable, a lurking variable, then we say that those two variables, x and y, are confounded. They're confounded. They're confounded when their effects on a response variable cannot be distinguished from each other. Okay, so let's take a look at some examples. So in each example below, what's the most likely lurking variable? Okay, some of these are obvious, some are not so. Let's take a look at one of the most obvious ones. This is a long-standing and well-documented and well-used example of association not implying causation. If you plot shoe size of children against a measure of their reading ability, you see a pretty good relationship. Does that make sense? Should there be anything about your shoe size as a child that makes you read better? No. Okay, what's going on here is that as children grow and their shoe size increases, they spend more time in school and their reading ability increases. Shoe size is not directly affecting reading ability. These two variables, shoe size and reading index, are confounded by age. As children get older, their feet grow, but they also learn to read better. All right, that's an example of association not implying causation. Another one, strong positive association between the number of firefighters at a fire site and the amount of damage a fire does. The more firefighters that show up to fight a fire, the more damage the fire does. Well, if that were the case, you might think, well, I don't want to call the fire department to fight my house fire because they're going to make it worse. No, what's really going on is that large fires require more firefighters to put them out, to combat them. Smaller fires require less, right? So larger fires, more firefighters show up to combat that fire. The fire also does a lot more damage because it's a bigger fire. So the number of firefighters that show up and the amount of damage a fire does are not causally linked. There's a confounding factor there. Larger fires do more damage. But also larger fires need more firefighters to fight them. All right, last one is not so obvious. There's a negative association between moderate amounts of wine drinking and death rates from heart disease in developed nations. Okay, we've all heard this, that if you drink moderate amounts of red wine, you're supposed to have heart healthy effects. So maybe that's a relationship. It could be that there are polyphenols or something in wine that, are actually good for your cardiovascular system. Not sure that that's been well documented, but it could be. What else could it be? Could also be, for example, that if you lived in a developed country like the US and you're able to afford red wine, a $10 or $15 bottle of red wine at the grocery every week, it may be that you're more affluent than somebody who can't afford that. And if you're more affluent, you probably have better access to healthcare. You can probably afford a gym membership, or you can probably afford to build your own home gym, that kind of thing. Maybe you have more leisure time for working out, exercising. You see how there are lots of things that could play into that and actually result in an apparent association between you drinking more red wine and being a healthier person. Whether or not there's really a direct relationship between red wine consumption and heart health in the first place. But there are lots of potential confounding factors there, socioeconomic status being one of them. Okay, so how do we establish causation if there are these potentially confounding or lurking variables that could, sort of get in the way of what we're trying to see here, the patterns we're trying to see? Well, basically, we can establish causation from an apparent relationship between an x and y variable if the association is strong. Okay, so that's a good indication. If we have an R squared of 90% or better, that's a good indication that maybe there really is a strong relationship between x and y. Is that association consistent? Every time we look at a data set about two variables, do we see it, right? Every time you collect data, a new set of data on these two variables, do you see it? If so, that's an indication it might be a real association, or causation might actually be there. Are higher doses, say with a drug, associated with stronger responses? If so, that's a good indication that we might have a real cause and effect relationship going on here. does the alleged cause precede the effect? If you have a blood alcohol content, have you already consumed beer or wine? You have to consume alcohol to have a BAC. If you haven't consumed alcohol, you can't have a BAC. So we have to make sure that the alleged cause precedes the effect. If it doesn't, then that's an indication that there's no relationship. And finally, is the alleged cause plausible? Does it make sense in terms of what we know about the system that we're studying? Okay. So generally speaking, if we can check off all of these different, or these 5 different characteristics, that's a pretty good indication that the apparent relationship is real and not confounded by some lurking variable. An example, lung cancer is clearly associated with smoking. We see high rates of lung cancer with people who have smoked, okay? Now, it's taken 20 or 30, or in some cases more, 40 years to really nail down that association as being real and not a result of some lurking variable. For example, what if there were a genetic mutation, a lurking variable, that simultaneously caused someone to both get lung cancer and become addicted to smoking? Well, if that mutation weren't known, but it were a real thing, its effect were a real thing, then there might appear to be a relationship between lung cancer and smoking, when really there's not. They're both being driven by that genetic mutation. We're pretty sure that there's no such mutation that does that. And again, it took decades of research and accumulated indirect evidence to reach the conclusion that smoking does indeed cause lung cancer. These things have to be, these possible lurking variables have to be sort of eliminated through trial and error and continuous study before we can actually say that relationship is real. Okay, and sometimes it takes decades for that to happen, as it did in the case of lung cancer and smoking. All right, that's it for chapter 4 then.